Hello all and good morning everyone. This is a demo for a MedGemma model which is by Google, and the reason of this demo is Kaggle. So Kaggle has hosted this competition via Google, and I am just trying to demo the MedGemma model. I wrote the code for this to show how MedGemma model is useful. So the problem statement over here is in the rural areas when you have any skin issues, right? There are no doctors, there are no much derm care doctor which can tell you whether it's a cancer or not. So this is the model where we can use it where there is no internet. So basic thing is it will work locally. Only internet is needed only when you are uploading or loading the model Gemma, MedGemma model, and with the help of HF token. Otherwise, we don't need internet, and that's the plus point. And plus, it will access your image, whatever you're putting it via a phone, via browser, and you access the image. That is the first stage. Then it gives you the findings, what has happened, basic findings. It asks the follow-up questions and also give the recommendations along. Let's see how it works ahead. So I am just uploading a dummy image. Do not just judge me on that. It's just a dummy image, and think that it is a lesion which has occurred on the skin. And then I'm clicking on access image. So when I click under the hood, MedGamma model is used. MedGamma is basically for the vision and large language model, vision encoder, and a large language model which is a multimodal in understanding, and it understands the image. Basically it tokenize it, and also the large language model, obviously it was a text interpreter, so it gives a visual assessment as well. Along with that, it gives you some follow-up questions. So for example, I said I just said no for every question. That no, I don't have any itchiness, I don't have any bleeding, no, I don't have any lesion, such kind of a thing, and no in family history. Then it will just give you monitor at home or reassess in 2 weeks, just a general information. But as and when I say yes, it lasts for 3 months. And then I said yes, yeah, it is bleeding and itchy and crusted. And yes, it's in family. If I say, then basically it will say go to an urgent care with a red mark, and seek 24 to 48 hours. And if I say just normal, yes, I don't mention any details about it. I mean, it's just a normal where you don't understand anything, whether it's an urgent or it's a generic thing. Then it gives you can visit the, so basically a recommendation triage. And this is done very much locally. I'm using right now CPU, so this is just a demo mode. When you will use TPU, it will really call the model and does it. Now, what is happening behind the scene of everything? I'll let you know. This what happens when you click on access image and everything. So this is my code, and in the code you can see here we the repo is Sanika Kaggle dump screener. And in the repo basically has this app folder. It has the model folder which does the fine tuning. I have shown how fine tuning can be done, how inferencing is done, evaluation is done. And then you have main.py which orchestrate everything. You have UI components which is a gradio UI which is being used, and inferencing which plays very important role, because we are what are the user assessment inferences, what are the triage recommendation, that all things are there. And we have run.py which runs in one Python command. So let's see what happens in main.py. So in main.py, basically it orchestrates everything, and it's a gradio blocks layout, which is very much recent one, which I have coded for. And when you click on access image, right, upon clicking on this particular button, behind the scene, we have MedGamma model, which picks up and it calls the inference.py. So now when it calls this inference.py, exactly what is happening? If you see, inference.py has this user assessment user text. So it always gives you this particular structured format. and in the and in this is the brain where it wraps medgamma and enforces production grade constraints, this particular file, and it's multimodal formatting with a deterministic inferencing. Now what happens when I say when the function is build a message. Now medgamma expects this messages passed in a structured object and not in an embedded inside text. So it construct the message, and it is checks whether it is not equal to RGB. RGB is red, green, blue, which every laptop can understand that particular thing. And we also then normalize this RGB. So basically, it is used, and then we have something called as assessment user, which I was talking on. Assessment user text. So we force the model to respond in a raw format, raw JSON with a fixed keys like condition, category, confidence, key features. These we are enforcing it. This is critical because it prevents LLM from producing free form text that breaks UI into downstream logic. Then we have this run inference.py, which has a very important place because again in the run inference we have evaluation model which is very much deterministic. And where is it? One second, let me just show you that. Yeah, this is the function. So it is very much deterministic. It calls model.eval. So again, along with model.eval, there is no gradient. So that disables the training action. So here, if you see, torch.no gradient is there. And then we have model eval as well, model.eval function. So this will help in disabling trading training time behavior like dropout, which is essential for consistent output. So we do not need that. And of course, no gradient is there. So we can compute no gradients, allocate no backward pass memory, and this inference is only strictly made on forward pass. And also there are tensor device correctness as well. Then thus giving you the clean output. Then you have this UI component level, which has all the UI components. So I'm not getting deeper on that. Then we have called as baseline inference.py. Now this is again a very much important because here we have evaluation. So in the evaluation, the script runs med gamma in a zero shot classification setting on ISIC data, and we load the metadata basically here. So we are loading the metadata in a CSV format. For each image, we run this deterministic inference and we calculate the accuracy and F1 um, we then compute the accuracy and micro f1. So when we and why we need this micro f1, because it is important. It weights each class equally, which is very critical when class frequencies are imbalanced, right? So we save the CSV and matrix the JSON and then generate the confusion matrix basically, and then we have this model comparison PNG as well. Also I have this fine tuning. We load this, for adoption we use QLoRa style fine tuning model, and I have made sure we are using this real time adapters of the QLoRa on this particular model. I had also load MedGemma in 4-bit quantization to reduce the memory and then call this particular function. And we are attaching these LoRa adapters to the highest leverage to attention this Q projector, V projector, and key K projectors. So LoRa trains the low rank metrics basically in this, and we are using the tiny fractions of parameters on this and then ship to that. But I want to be very much transparent in this version. The training loop is abbreviated to a local demo. So if you see my in .env, I have local demo true. I'm not going into that because I have my own tokens, but the adapters and injection and quantization technique is fully in place, and I'm looking forward forward for this. And then we have comparison, as I mentioned, and then I have also readme file so that it can give you the stages, like how it is made, what comparisons I've made, what performance it is doing, what is the problem, and everything. So thank you for watching.